Hey guys, welcome to the sixth session of number systems in the playlist of quantitative aptitude for mbaentrance exams. And as I have been saying since the first session itself, that this topic is going to be the core foundation for all of these exams and even your campus placement and several other aptitude exams. So this will go in hand with all the topics and questions. And so far, we have covered prime numbers, type of numbers, number tree, factorization, and even prime factorizations, right? So let's take it up a notch in factors topic particularly. So ever wondered, what if the examiner asks you to find the total number of factors for any given number? Or rather, you need to find the total number of factors for solving some other part of the question. In DILR or for other quant type questions, you need the total number of factors so you can proceed with your next operation. So how will you go about it? Well, let's solve it with the example. Let's take 528, and from here let's do the prime factorization, and I can clearly write 528 is equal to 2 raised to 4 into 3 into 1 into 11 raised to 1. That much is pretty simple, we all know how to do it. But one thing to notice here is, rather than dividing 528 with 2, I have divided by 4. By doing so, my number of steps have decreased. So the thing that you need to grasp or understand here is, you need to do smart prime factorization. So your time wasted here would be minimized, because for 4 I clearly know it is 2 square. So if I am getting 4 square, I can directly write 2 raised to 4. Even better if you know that you can directly divide this by 16. Even best case, if you can directly divide by 16, you know 528 is in 16 table, go ahead. But just remember to replace 16 with 2 raised to 4. Now, coming back to main topic, the total number of factors for this number, how do I find it? I just clearly add 1 to all of these factors power and multiply them together. So 4, 1 and 1. I will add 1 to each of them and multiply them together to end up with 20 as my TNF. TNF is nothing but total number of factors, just a shortcut to writing them. And it is indeed a very important part. Even in DILR, when they will be giving you too much information. So when you are solving that, if you go about writing it completely, like some random names or some code, rather than writing it full, just make some small code or key which will help you identify that this is for this, this is for this. It will save much more time. This is a good practice to make such sort forms or keys for big terms. So total number of factors is TNF, and for our case it will be 20. Now the reason for adding this 1 is to incorporate the effect of power of 0. The actual possible values which I can put in as the power is 0, 1, 2, 3, 4, 0 and 1, 0 and 1 for 2, 3 and 11 respectively. So to account for that 0 as the power for each of these numbers, I have added 1. Nothing more, nothing less. And if you put a little common sense in this, you will notice, if you take, let's say, 2 raised to 4, only take 2 raised to 0 out of this. You will be left with on the other side 2 raised to 4 and 3 and 11. So 1 into that whole 2 raised to 4, 3 into 11. That means 1 into 528. That is one of your factors, 2 raised to 0. Then similarly, 2 raised to 1 is your factor, 2 raised to 2 is also factor, 2 raised to 3 is also factor. So that's why by powers, we are getting our number of factors by multiplying them together. This is nothing but permutation, just simple permutation combination. And we added 1 to incorporate that possible value of 0 as well. So that pretty much sums it up. But what if they ask about the total prime factors? Well, they are in front of your eyes. Total, obviously, they are 3, 2, 3 and 11. So TNF is dependent on the power of the prime numbers, and prime factors themselves, well, they are the base. So you got two things cleared out now. And make sure after this, if you are making notes, after this section, do leave 2 to 3 pages, because there are several topics which are related to this, and I will be taking the same example of 528 to elaborate them or explain them. So it would fare much better if you leave space after itself and start the calculation that you are going to be practicing from the 3rd page or 4th page onwards. Now, before we move into calculation part, there is indeed a drawback if you are wondering about it, that it is not recommended for simple and small numbers which you can calculate orally, like 12 or perfect squares like 36. You can directly get there total number of factors directly, and it's not worth wasting time. But yeah, if you are uncomfortable with calculating the total number of factors, then and you notice that by this method it is indeed fast for you, then you are free to go ahead. But I'd recommend, as a CAT aspirant or MBA aspirant, such numbers of perfect squares, at least prime perfect squares, you should be able to do TNF orally without prime factorization. So that is not as such a drawback, but just a good thing to do, that you find TNF for such small numbers orally. In long run, it will be helpful. Now, let's try. You need to find TNF of 9, and if you are doing this like this, I wouldn't recommend it, because whenever I see 90, I clearly get the picture of 9 into 10. Now 9 itself is 3 square and 10 is equal to 2 into 5. So I got my prime factorization. I didn't even need to bother about looking at this division table. So that's one example of smartly splitting the number in two factors, so you can directly get the prime factors from it. And you don't need to, find this division table every time for all numbers, because it is quite time consuming to make it and again write all the factors. So I think this is a much better way to smartly split the number. But if you are not able to think it up, just go ahead with the division table. It is better than doing nothing and just thinking about it in the exam hall. Okay, so anyways, our main concern was to find the TNF. From here I can clearly see 3 has a power of 2, so I will add 1, and 2 and 5 both are having 1, so I will add 1 to all of them. So 3 into 2 into 2, that will be 12. 12 is my answer. Let's move ahead. Find TNF for 576. Now, if you remember the squares and cubes correctly, you will instantly notice 576 is a square of 24. And 24 I can split like 8 into 3. Now, many of folks will try to split it like 6 into 4. But again, 6 and 4. So 6 will be 2 into 3. So I need to again shift that 2 to 4. That will again give me 8. So rather than going the roundabout way, I think this is much better split. 8 into 3. I'm directly getting my prime numbers from this, because 8 is 2 cube. So this is the better optimized way of smartly splitting them. And whole square, because 24 square. So yeah, I got my value 7 into 3, 21. And of course, when you're doing TNF, this is, just one way of smart verification, that if you got the odd total number of factors now, then your calculation is right, because 576 was clearly a square. So I got an odd TNF, and I am sure that yes, I didn't make any, calculation misstep. It is a kind of verification that I did my calculation correctly, because I knew 576 was a square. So my TNF must come odd number. And reverse is also true. If a TNF of some number is odd, then it has to be a square. Now obviously, identifying square is also possible from the prime factorization form. If all of them are multiplier of 2, it is indeed a square. But if you didn't notice till then, you can also notice from TNF. That is also one way. It is also property of squares. So yeah, just one more bit of information which might be helpful in any time. Now, how do we go about finding the odd factors only? I am only concerned about the odd factors. So let's take that same example. You can try from empty space that you left behind. I will just be writing that same thing again. Till here we have done it, right? Now, for a number to be odd, what is the only thing which will prevent it from being odd? Or we can say which will make it even? That is presence of 2. Any number can only be even if it has a multiplication of 2 in it, or 2 is a factor for it. So simple thing would be ignore the 2 completely. In our case, we will ignore the power of 2 completely. So we will be left with 3 and 11. Both of them are having 1 as the power. So I will add 1 and multiply them. That will give me 4. And that exactly is my answer. So out of these 20 factors, only 4 are odd factors. That is my answer. And even factors, I can just subtract. If 20 is the total factor, 4 are odd. Obviously 16 are going to be even, right? Okay, as impatient as ever I see. Just let me pick this up.
Hello sir, Kelvin here. Sir, but what if in some exam where time is less and we want to directly find total number of even factors of that number? Is there a shortcut?
Well, I pretty much predicted it. Anyways, I know that many guys are lethargic, so you need a shortcut for even factors as well, right? Because yeah, I agree that in some exams they might directly ask find the total number of even factors for this number. In even CMAT and SNAP, it is quite a possibility. So I will just demonstrate how to do it. Let's take the same number 528, and for it to be a even factor, what is the condition? It has to be at least having one, at least having one 2 multiplied to there. And if you think logically, for permutation combination point of view, what has changed? The power of 2 cannot be 0 now. It has to be at least 1. So that's why I will not be adding 1 to the power of 2, and I will keep it as it is. And that will give me 16. So yeah, that's my answer. The only drawback is you need to mug up this or extra method or formula, you can say. But if you think logically from permutation combination of view point of view, I think this much is pretty clear. If you need even t factors, just keep the power of 2 as it is and do your general process of TNF for other prime numbers. So you got how to find TNF, how to find the total number of odd factors, and how to find total number of even factors. With that said, I think it's time for some practice. So let's go ahead. You need to find TNF of these two number, total number of odd factors as well as total number of even factors for. So in total there are 6 questions. And before you start, just a heads up that if you ever notice a square of a prime number, mind well, square of a prime number like 2 into 2, 3 into 3, such that all of them will have exactly 3 factors. Nothing more, nothing less. That is a fact. So if you ever encounter such a number, you can directly write 3. No need to do prime factorization. That's why again, squares and cubes are important. And I think so far you must have solved them yourself. So let's verify your answers. For 1029, best way to split would be 3 into 343, because 343 is the cube of 7. So yeah, so 7 cube into 3. So powers of 3 and 1. So I will add 1. I will be left with 8. As for 889, the only way it can be split is 2 into 449. Apart from that, there are no methods to split because 449 is a prime. You can even check it on Google. So yeah, TNF would be 4, adding 1 to both of their power. Now for odd factors. Now 1080 is a very smart split because first of all, 1080, 108 into 10, so you directly got 2 into 5. Now 108, I clearly remember it is 12 into 9 because up to tables up to 20 I know them by heart. So 12 into 9 would be my case, and as I'm only concerned about odd factors, I won't be looking at this 2 at all. But what I am concerned about is the 3 inside the 12. So that 3 will go with 9. So I will be left with 3 cube into 2 raised to something into 5. I'm not concerned about 2 at all because I know I have to find odd numbers, odd factors. So 3 will have power of 3 and 5 will have power of 1. So again I will be left with TNF of 8. As for 369, obviously I can clearly see 369 itself is an odd number. So there would be no multiplication of 2 involved. So its TNF itself will be odd factors. All of its factor will be odd, you can say. So TNF will be the same as odd factors. Now, as for the even factors, this was quite a tricky question. I thought many of you might have directly written it 0. I hopefully think so. But if you tried to do prime factorization and then ended up with a 0, I think that's quite a sad thing, or rather disappointing. Because at a glance you should clearly know 943 is an odd number. That means there was no multiplication of 2 involved in this number. So in any case, it is not possible for it to have even factors. That's why you can clearly write 0. No need to do prime factorization. Now for 484, it was quite tricky, I must agree. But here also there is a trick. Whenever there is the same number at the start and end, and in between all numbers are double of itself. For here, our example 4884, 4 is at start and end, and between all numbers as double of even 48884. In such a case, just consider the n2 number as the number itself. That would be your best bet. That means 4884, I will directly divide by 44 the first time. Even just for other example or instance, consider 3, 6, 6, 6, 6, 6 and 3 at the last. No matter how many times the number is repeated, but the end first and last number, that would be your divisor. That is a smart trick that I learned from my teacher back in 7th or 8th standard. So that's quite a helpful trick. Even for let's say 3 or 2, 2, 4, 4, 4, 4, 4 and 2 at the end. That means I can directly divide it by 22. That would be the fastest way. Any case, so 484, I first divided by 44, which is 4 into 11. I clearly know that. And I will be left with 1, 1, 1. Now, 111 is quite a unique number, which I clearly remember is 37 into 3. Only because it was a unique number. I thought it might be prime. That's why I remember this, that 37 into 3 was 111. Any case, we are interested in the even factors of this number. So I got them from 4, which is 2 square. And I know very well for even factors, I need not touch the power of 2. That means 2 square. The 2 at the top will remain as it is. And for 11, 3 and 37, all of them are having 1 as power. So I will add 1 more and multiply all of them together. So 16 is my final count of all the even factors. So I hope you guys enjoyed this session. See you again next time. Thank you.